Great. So it is a real pleasure to welcome Matt Hastings to our colloquium. Many people who joined this Zoom call, they may know Matt's results. He worked in a number of different areas. He worked in various on various very interesting quantum information type problems, additivity, super additivity of classical information. Those people who do that, they know his 2008 result very well. He also worked on the stability of topological quantum order under local perturbations, which was led to lots of interesting insights. Then he worked on Lieb-Schultz-Matisse theorems and generalizations for higher dimensions, and its implications for topological quantum computing and quantum mechanics. So Matt has done a lot of interesting work, and today he will present us with yet another interesting result, which is about sum of squares for fermionic systems and the SYK model. So Matt, the floor is yours.
Okay, thank you. Thanks very much for the invitation. It's great to have a chance to talk about that. This result is now, I don't know, about 2 years old or something, but it's still something that I'm super excited about and spending a lot of time thinking about. So hopefully I'll convey the excitement. I'm not quite sure how to convey it, so I hope that I'll get across why I'm interested in it, but I'm not sure I'll succeed. This is joint work with Ryan O'Donnell, and I might talk about some more recent stuff I did too. So I really want to encourage people to ask questions, because Ryan also has a talk on this, which is on YouTube, and Ryan, I think, is better at giving talks than I am. So if you just want to sit quietly and watch a talk, you can just go watch his talk. But so hopefully with questions, this will be useful. So this is about the sum of squares method and the SYK model. And I kind of need to say what both those things are. In brief, the sum of squares method is a method for proving some properties about Hamiltonians, deriving, for example, some property of the ground state, energy, or other properties of a Hamiltonian. And it's a non-perturbative method that's analogs of it are used in classical computer science for all kinds of things. And the SYK model is a model of interacting fermions, which is sometimes regarded as being like the most strongly interacting, most entangled possible Hamiltonian you could write down. People make connections to gravity and black holes and so on. So in a sense, one method is kind of made for the other, because sum of squares is kind of like the most non-perturbative method there is. So I'm going to talk about both these, but let me just, to get started, let me talk about the sum of squares method. So let's say someone gives you a Hamiltonian, some local Hamiltonian acting on a few particles. It could be, this method was originally a method in classical computer science. So it could be just some Hamiltonian like a classicalizing spin glass. So something like this, I'll write it using quantum notation, but this would be a purely classical model, like some Ising spins represented by some Pauli operator Z on each spin. I indexes spin, and J is some matrix of coupling constants. And potentially this model is, has a spin glass phase, and in that spin glass phase, it's believed that it's NP hard to, well, it is provably NP hard to figure out what the ground state energy is. It's believed there's no fast way to figure out what the ground state energy is of this model. But there's a powerful method called the sum of squares method. And so the sum of squares that can yield important non-perturbative information about this model. And the sum of squares method is basically say, well, let's say we could find this H. Suppose someone could go find a decomposition of H as a sum of squares. So I'll have some discrete index now alpha. And you could write it as a sum of squares of operators. O alpha would be some operator, some linear combination of these Z's in this particular case. And plus a scalar. So lambda would be a scalar. So suppose you found such a decomposition of this model. Then you would have proven, this would imply that the ground state energy is at least lambda. Because each of those squares, each of those O alpha squares is necessarily a non-negative operator. So this would be a proof that the energy is at least lambda. So, how could you do such a thing? Well, I mean, one particular case, for example, is if you had, I'm probably going to do this wrong on the fly. I should have worked out all the signs in this case beforehand. Let's say you had 3 spins, and we'll call them 1, 2, and 3. And the Hamiltonian was like Z1, Z2, plus Z2, Z3 plus Z1, Z3 if you had a Hamiltonian that was of that form. So it's just an antiferromagnet on the 3 spins, positive coupling constant. So it's an antiferromagnet. It might be possible to write this thing as a sum of squares. And a natural way to think about it is, well, there's this cyclic symmetry, right? Cyclically permuting the 3 spins. So natural choices of these operators, so alpha 1 would be like the combination Z1 plus Z2 plus Z3 squared. Another choice would be like Z1 plus omega Z2 plus omega squared Z3 squared, where omega is a cube root of unity, and Z1 plus omega squared Z2 plus omega Z3 squared. So you might be able to find some decomposition in this form with some coefficients. This is just kind of like a natural guess. Oh, probably I would use some combinations that would respect the symmetry plus a lambda, and you can find such a decomposition, and this would prove you some lower bound on the ground state energy. Unfortunately, it would not be the best lower bound on the ground state energy. It would be the lower bound. It wouldn't really fully realize that it was frustrated. It wouldn't realize that if you point, you point one spin up, another spin up, and another spin down, it's the best you could do. It would basically get you the ground state energy if the spins were able to point off at some angles, like if they weren't Ising spins +1, -1, but rather they were kind of able to point, they were XY spins, like pointing this way, and this way. So it would give you a weaker bound on the ground state energy, but it would give you some kind of bound on the ground state energy. You could improve this method if, here this operator O that I've written is just a linear combination of these Z's. You could improve the method if you allowed O to, for example, be scalars, linears, and quadratics in the Z's. That would allow you to improve the power of the method. If you improve, and you might say, wait, how does that work? If the O has a quadratic in the Z, O squared is going to have a 4th power in the Z. But it might turn out that whatever 4th power in the Z you write down happens to cancel between all your terms, and you still have such a decomposition. And if you allow even more and more general terms of O, cubes of Z's, and so on, the method can become more and more accurate. And it's actually not hard to show that at some order, it must become perfectly accurate, because let's say the ground state energy of H is some E naught. Suppose it's some E naught. So we have H greater than or equal to E naught. Well, then H minus E naught is a positive operator. And so you could say H is the square root of H minus E naught squared plus E naught. And this H square root of H minus, yeah. Question? Is there a question? No. Okay. So so the general idea is that you have some approximation that when these O are just linear or something like that, gives some information, and as you increase their order, it gives more and more information, and at some order it will become exact. Now this method is there's an important question in classical computer science. Like, it's actually believed that at this simple linear order, that this is essentially as good an approximation algorithm as you can have. It gives the best possible approximation for this kind of this particular problem with quadratic coupling between the spins. And higher order may improve on it for specific problems, but for the approximation ratio, the ratio between how well it does to the true ground state energy, this is as good as you could possibly have, and it's believed no polynomial algorithm could do better. But in specific cases, going to higher order may do better. So there's also been a lot. Yeah. Was there a question?
Is that requiring the unique games?
Yeah, that's under the. I said believed. Yeah, I mean that's the unique game conjecture implies that. Yeah, that's the best possible. And there's been a lot of interest in the power of this method. Sort of how badly can you fool it? So this method at this order, the order that we would call this a degree 2 sum of squares, because each of these O alpha is a linear combination. So the square of O alpha is a degree 2 operator. It sort of can't get fooled too badly for this particular problem. For this particular problem, if the energy is something, it proves some lower bound on the energy. So it proves some number that's lower than it, but it never proves too much lower. And you could say sort of how badly it's fooled is how much lower in energy it proves. And a way to show that this method never proves too much lower in energy is I won't go into it. There's a way of sort of rounding its solution. It gives some solution, and there's a way of turning its fake solution into a true actual choice of Zi, which has some higher energy. So it finds a certain energy. There's some energy close to what it finds, which is actually a state that it could have. And that state has to be at least the ground state. So the true ground state has to sit somewhere in there. So it can't be too badly fooled. And there's a lot of work on other models. Like if you start adding in cubic couplings, if H now starts to have something like Ji, Jk, Zi, Zj, Ck, you may ask, how badly can this model get fooled? And the answer at that point, once you get to there, is you can fool sum of squares incredibly badly. You can have models which are essentially very frustrated, and the best solution is hardly better than random. Yet the sum of squares method at any fixed degree thinks you can like basically satisfy every term simultaneously. So it can be fooled very badly, but it's believed basically every method can be fooled very badly. This is sort of believed to be the best possible method. So somehow there's some transition between degree 2, we can get a reasonable approximation, and under this unique games conjecture, it's thought to be the best possible. At degree 3, suddenly it's thought that like there's nothing you can do. It's just you just throw up your hands. Okay, so but we are quantum physicists, so of course we want to do a quantum version of this model. So for a quantum version of this model, well, you might start having a Hamiltonian that involves like x1, x2 plus z2, z3 plus right? Like all kinds of different Pauli terms that don't necessarily commute with each other. And you can still potentially write down a decomposition of H as a sum of squares. An important point here is that actually it gets significantly more powerful to allow the operator O to be non-Hermitian. And so you have an O dagger O, because things may not commute with each other. O might not commute with its adjoint, and plus some scalar. And then again, that's a proof that the ground state energy is at least the scalar. So this is an important method. Now, one thing that I've kind of glossed over, I guess I should emphasize, you might be saying, how do you find this decomposition? I've said it's a good method. It's a polynomial time algorithm. The important point is that finding such a decomposition. So what does it mean to find such a decomposition of H as a sum of squares? Well, you have some choice of these O alpha. You have to verify using that particular choice gives you the same thing as H, and that will require using commutation relation. So for example, if somewhere in this O dagger alpha, O alpha, you see some Zi, you can know, oh, that's the same as 1 because Z squared is 1. If you see XY plus YX, you know that's 0. So using the commutation relation. So there's some set of like linear constraints on these sum of squares that implies what you want. And subject to those linear constraints, you want to maximize this lambda. You want to find the best possible proof. Different decompositions will give you different values of lambda. And it turns out that this is a semi-definite program. I'll say a few words about what a semi-definite program is. It may be more convenient to explain the semi-definite program by the dual formulation of this. What is the dual formulation of this? So semi-definite just like is an optimization method. It's a convex optimization method. There's a certain problem, and given the problem, there's a so-called dual problem, and one involves minimizing something, one involves maximizing something, and the minimum of one problem is the same as the max of the other problem. So you kind of sandwich the true solutions in between the two of these, the min and the max. So one problem here is find the best possible decomposition of the O dagger alpha to maximize lambda, to make it as big as possible. And that's a semi-definite program. Another solution, another method, this is the dual of it, or the dual of that problem, the two problems are called the primal and the dual, is based on what's called a pseudo expectation value. What is a pseudo expectation? Well, suppose you have someone says, hey, there's the ground state energy of H is actually such and such, and I'll prove it to you because here's a quantum state that has that. So what properties might you ask about the quantum state? Well, one thing is you might want to ask about various expectation values of various operators O. And you might say, okay, tell me the expectation value in your state of all operators O. Well, that would be a huge thing to write down, right? There's exponentially many such operators. So you might say, well, tell me the expectation value of all operators that are linear, quadratic, degree 3, degree 4 in these Pauli operators, X, Y, and Z. And now that's a polynomial thing. You could write it down. That's, okay, n to the 4 because you're up to degree quadratic. So you might have some quadratic, so n to the 4 different such things. And you ask them for that. And what do we know that these expectation values obey? So someone gives you this list of expectation values of all these operators up to degree 4. You'll know that it obeys certain commutation relations. So if they tell you the expectation value of X times Y, that's minus the expectation value of Y times X. You also know a certain positivity. You know that the expectation value of O dagger O is greater than or equal to 0 for any choice of operator O. So if you have a degree 4 operator, which can be decomposed as O dagger O for some degree 2 O, it has to have a non-negative expectation value. So if you take these expectation values and you write it as a certain matrix, I'm going to write it as a matrix Mij, which will be the expectation value of some operators O dagger I, Oj, for some particular choice of OI that I pick. OI will be some basis of operators, in this case up to degree 2. I know that this matrix M is a positive semi-definite matrix because of this requirement. This requirement implies that this matrix M is positive semi-definite. And I know that this matrix M obeys some linear constraints given by the commutation relation. So like expectation XY is minus expectation YX. And that's expectation IZ, which is, and so these operators O dagger I would be like all up to degree 2 or whatever, up to some given degree. And given this matrix, if someone gives you this matrix, you can compute the expectation value of the Hamiltonian, assuming, because the Hamiltonian is some operators, and this matrix will tell you it's their expectation value. So what you're trying to do is you're trying to have a matrix subject to some linear constraints that's required to be positive semi-definite, and you're trying to minimize a certain expectation value, which is just a linear function of that matrix. And that's what a semi-definite program is. I mean, that's exactly the definition of a semi-definite program. Minimize linear function of a matrix, subject to linear constraints on the matrix, and subject to the matrix being positive semi-definite. So you have these two problems, the primal and the dual. One is to find a sum of squares decomposition, and one is to find these pseudo expectations. And these can both be solved in polynomial time on a classical computer. Now, the time is polynomial in the size of the matrix. The matrix is polynomial in the system size. So unfortunately, the polynomials may get large-ish as the degree goes up, but it is an efficient method and can be applied in practice. So that's the sum of squares method. Now, so Ryan and I were kind of thinking like, what's the power of this and how badly can you fool this method? And we started thinking about quantum problems, and these kinds of quantum problems where you have like just qubits, X, Y, Z, and so on. In a sense, the fooling question is precisely the same as the fooling question classically, if you're only interested in constant factors. Like if you want to approximate this thing to some constant factor, what you could do is you could just randomly on each site pick a basis and say, oh, I'm going to like require that the spin be only on the X basis on this site, only on the Z basis on this site, only on the Y basis on this site, and look in that. So I'll only keep terms that involve like X on this site, Z on that site, Y on that site, just choosing it randomly. And that turns it into a classical problem. And each term would then have like a 1/9 probability of surviving this, because it would be like X1, X2, did I happen to pick that I'll keep the X basis on site 1 and the X basis on site 2. So you won't get much worse off. If you have a classical approximation, you have a quantum approximation, it's only factor of 9, which is order 1, although kind of a big number of order 1 worse. So the question of like, can you really badly fool these problems where it's not even getting close to the right answer is the same for these qubits as it is for the classical degrees of freedom. But there is another problem that you might consider, which is fermions. And fermions are interesting. And I'm going to use, and probably I need to give an intro here too, I'm going to use the SYK model as a test bed. So the SYK model is a model of fermions. We're going to have some matrix tensor, JIJKL, which is just some tensor of scalars. And we have some operators, gamma I, gamma J, gamma K, gamma L, which are, these are Majorana operators. These are operators that obey certain anti-commutation relations. So gamma I, anti-commute gamma J is going to be 2 delta Ij. These are Hermitian operators. So this is the SYK model. It's degree 4 couplings between these gammas. Actually, it's degree 4 couplings between these gammas where this J is chosen from a particular distribution. And these gammas are Majoranas, or this would be Majorana operators. This is, it's really no different to think, we might be, depending upon what you do, you might be more used to thinking about fermion creation and annihilation operators, psi dagger and psi. These Majorana operators are not so different. If you have a pair of operators psi dagger and psi, you can map it to a new set of operators, gamma 1 and gamma 2, where gamma 1 is like psi dagger plus psi with some, depending upon your normalization, like 1/2 or 1/√2 in front. And gamma 2 is I psi dagger minus psi. And again, like I say, there's some factor of 1/2 or √2 or something like that that you can check to make sure that they get the commutation relations. And if you have n fermions, so you have n creation operators and n annihilation operators, that would be 2n Majorana operators. Each fermionic creation operator gets mapped to a pair of Majorana operators. So these Majorana operators are just a little more convenient if you don't have particle conservation. So you don't have any kind of like particle hole symmetry or anything like that. So you just forget about all that symmetry and you just write it directly in terms of these combination of creation and annihilation operators. So in the SYK model, it's a model of this, and the J is completely anti-symmetric. I mean, if it weren't, it would, so it would, you just pull out the completely anti-symmetric part. And entries are Gaussian, subject to that complete anti-symmetry, are Gaussian, and they're just Gaussian random variables. I'm going to choose, this is the normalization we used. It's a little more convenient for computer science. It's less convenient for physics. It's not the one in the physics literature. I'm going to choose that the L2 norm of J is equal to 1. So that is that the sum of the squares of the entries of J is equal to 1. Conventionally, in the physics literature, the L2 norm of J winds up being of order square root n, which just changes the scaling of some of the energy. So if some of the numbers I quote seem different from the physics literature, that's why. And this is the SYK model, and it's, like I say, believed to be incredibly strongly interacting. So now, of course, there's different SYK models. I've taken degree 4, so this could be called SYK4. SYK4, because it's degree 4. There's an SYK2, SYK6, SYK8. There's actually also odd ones too, which are a little weird. So SYK2 is you only have quadratic terms, gamma I, gamma j, jij. So let's think about how hard these methods are. Of course, these models are. Of course, since it's random, the hardness is a different thing. Actually, with high probability, we know what the actual energy is. I mean, there's a conjecture for the exact value of the ground state energy that's not proven. The ground state energy has been proven to lie in a certain range for the SYK4. But we could ask, how badly could we be fooled if you just had an arbitrary degree 4, degree 2, or degree 6 thing? So if you have a degree 2 problem, gamma I, gamma j, jij, this is exactly solvable. Like, it's actually easier quantumly than the corresponding degree 2 jij, zi, zj. It is exactly solvable. You can solve it perfectly. Now, because it's just free fermions. Degree 4 SYK, well, so an important thing is that given any classical model, I can encode it in this model of fermions at twice the degree. So the classical model jij, zi, zj can be encoded into a degree 4 Majorana model. How is this? Well, it's that you can encode a single spin into a pair of Majoranas. And so you can encode like Zi into a gamma 1, gamma 2 can look like Zi. And so you can take the degree 2 classical model and encode it in a degree 4 thing of Majoranas. So this degree 4 is at least as hard as that degree 2 classical. But we have an approximation algorithm for that degree 2 classical. We may wonder, do we have a degree 2 approximation algorithm for this degree 4? Ryan and I did not answer that in generality, but we did answer that we can prove some things about the SYK model. We didn't come up with a general algorithm for all degree 4. For degree 6, there's no approximation algorithm because there's no that always works, because there's none that always works for the degree 3 classical. Okay, great. So we have this SYK for Hamiltonian. So what do we know about this SYK for Hamiltonian? This is what I'm going to be talking about for a bit. The first thing one can guess is something about the ground state energy. One can guess something about the ground state energy and the lowest energy and the most excited state energy. And I'll just say actually just the norm of H. So that's the largest eigenvalue. It's less than of order square root n with high probability. With high probability meaning like with probability that gets close to 1 as n gets large. how can we show this? Well, we can show this by looking at, for example, the trace. Look at the trace of h raised to some power m. The trace of h raised to some power m is clearly an upper bound for the operator norm of h raised to the power m. Let's take m even. Because so that bounds how big the trace is. Now, if we look at the trace, of h, well, h is the sum of jij, gamma I, gamma j, gamma k, gamma l. So it's going to be some sum of like ji, j, k, l, gamma I, gamma j, gamma k, gamma l, then j, m, n, o, p, gamma m, gamma n, gamma o, gamma p, and so on, summed over all these different choices of I, j, k, l, and so on. It's going to be some like enormous sum where you have a total of m terms in this product here. And now we're going to average that over the choice of j. And when you average it over the choice of j, since the entries are Gaussian, all you need to worry about up to this anti-symmetry, which doesn't really matter, is that you're going to basically pair off. Like you're going to say, oh, this entry of j pairs off with that one, because you're going to get like a delta function. It's okay, so ijkl equals mnop. And you have a different way of taking these m terms of j and pairing them into m over 2 pairs. And then you have some sign, which comes from this absolutely enormous product of gamma matrices. But to upper bound it, we can just say that that sign is +1. And so that this is less than or equal to the sum over pairings. And then you have this expectation j squared, which from the choice is 1. And so it's actually going to be something like m to the m on 2, which is like an upper bound on how many ways to pair it. It's like m on 2 fact. Yeah, well, the number of ways of taking m things and pairing them off m over 2 ways. And then there's a factor of 2 to the n, which is the size of the Hilbert space, because we're actually like taking the trace of this operator. Then if you just pick, so then that tells you that combining this thing here to this thing here, that tells you that the operator norm of h is less than or equal to square root m 2 to the n on m. And if you just pick, the best is to pick n to be around m to be around n, and that gives you that square root n bound. So that gives you some upper bound on the energy. But this is an interesting kind of upper bound. This upper bound doesn't tell you anything about any specific instance. Like if I give you a specific instance, which I chose randomly, you can't apply this bound to prove that the norm of it is less than that. You know that if I really pick that instance randomly, the norm will be less than that, but you can't prove anything about any specific instance. So, one way to try to say, is there a certification algorithm? Is there an algorithm that maybe won't prove everything for every single instance, but like an algorithm that will take an instance and will either say, here's a proof that the energy is at most square root n, or I can't say anything, I decline to answer, but it will almost always give an answer if you chose it from this SYK distribution. And the answer is yes. We come up with one. We have one based on the sum of squares method. I'll just say some of our results before I say how they come from. So yes, we have a way of certifying this based on the sum of squares. So the sum of squares is reasonably powerful. It's kind of interesting what you need to do. You need to go to a slightly higher order, but the sum of squares is able to say that. You may also wonder, is there a lower bound certification method? Okay, so we know that the Hamiltonian has norm around square root n. If we're talking about the largest eigenvalue, we know that the largest eigenvalue has at most that. We're talking about the smallest eigenvalue, we know that the smallest eigenvalue has at most minus square root n. Can we bracket it the other way? Like, can we say, okay, well, the largest eigenvalue is at least this? We come up with a quantum certification algorithm for that. A quantum certification algorithm that has the same property. It will, on most SYK instances, it will output a variational state, and that variational state has expectation value for the energy that is of order square root n. And the quantum algorithm was actually highly inspired by the sum of squares method to find the upper bounds. So we have a classical certification one way and a quantum certification the other way. And now you might wonder, I keep saying, oh, this model is the most entangled model possible. You may wonder, like, okay, how do you know that? Of course, they talk about this, other fields of physics all the time, but is there some kind of like computer science-y, quantum information-y way to say that this is so entangled? And an interesting question is, is a variation, is a simple classical variational state. Like how could we on a classical computer prove something about the energy? And one way would be to write down a variational state that on a classical computer, we could efficiently compute its energy. And the simplest such state is a so-called Gaussian state. It's the ground state of a free fermion system, and it's not hard to show, and I'll show that. It was shown by other people before us that does not come close with high probability. That gives an energy that's only of order 1 rather than of order square root n. So it's far away from the true ground state. I just put a paper on the archive, which, among other things, extended it and shows that combinations of Gaussians under some orthogonality assumption under the Gaussians you take in the combination also cannot do well unless you have a super polynomial, a large number of such Gaussians. So there's like the variational states I know how to write down, you can show that they don't do well either. So it's kind of an interesting thing. Like we can show that there's no good classical variational state. There is this energy, but you can't show there's no good classical variational state, but all the classical variational states we know you can show aren't any good. So those are kind of the main results about this SYK model. So I'll talk a little bit about how we showed them, but let me just make sure, is everyone happy? Like, are there any questions or more questions?
So I have a question. So what are those pathological instances where, you cannot upper bound the norm by square root of n? Because this is obviously the average case result. Yeah,
I mean, so certainly there are instances where the norm may be much larger than square root n. It might turn out that there's no frustration. It might turn out that the Hamiltonian looks like lots of terms like gamma 1, gamma 2, gamma. It looks like we somehow coded some classical spin problem in there, like that Jij, Zi, Zj, and that classical spin problem happened to have no frustration. It might be something like that. That's of course very unlikely, and in that case, we might still actually be able to run this sum of squares method and prove something about the energy that was within a constant factor. So we don't know like how it does in worst case. Like, where does this sum of squares break down? Like, will it always break down or not for these kinds of methods? We don't know anything about that. It's an interesting question. Like, for the degree 2 classical one, it's proven that there's this, that it always gives at least a constant factor approximation if you sort of choose a correct definition of what you mean by approximation factor. We don't know if the same holds here or not, and I think this is an important question. But we do know that for this particular model, it's encouraging that for this model it can solve it. Other questions? No. Okay. Okay. So let me first talk about, I said that the Gaussian state typically does badly on this. Let me just first show that and then talk about, to kind of motivate like why you want these non-perturbative methods. We know now that the ground state energy, we know it's at most square root n, but you can kind of guess it winds up being of order square root n. The Gaussian method, so Gaussian state is a ground state of a free fermion Hamiltonian. And the nice thing about a Gaussian state is that if someone gives you a product of some like gamma 1, gamma 2, gamma 3, gamma 4, and you want to compute the expectation value of that in the Gaussian state, you use what's called Wick's theorem. I mean, this is almost the defining property of a Gaussian state. And what it is you sum over different ways of pairing. So it's the expectation of gamma 1, gamma 2 times the expectation of gamma 3, gamma 4, plus or minus, you have to work out the signs, gamma 1, gamma 3, gamma 2, gamma 4, and plus or minus gamma 1, gamma 4, gamma 2, gamma 3. I mean, it's not hard to work out the time, just writing plus or minus. It's some sign of a permutation that goes into working out. And in general, if you work out even higher expectation values, like an expectation value of 6 or 8 or however many gamma matrices, you just pair them off in all the different ways. Each way you pair it off has some expectation value. The defining thing of a Gaussian state is what is this expectation value of each pair of two Majoranas. That's how you compute higher expectation values. So if you want to know the expectation value of this Hamiltonian in a Gaussian state, well, you just have to sum these 4 pairings. And so let's just pick one pairing and bound it. And so we have some expectation Jij, gamma, gamma I, gamma J, gamma K, gamma L. And let's look at the particular, like the expectation gamma I, gamma J, expectation gamma K, gamma L, and then times Ji, Jk, L. And the nice thing about this is that, and summed of course over I, J, K, and L, is that you can regard this final expression I wrote here as being a kind of matrix vector product. So I might want to actually, it might be more clear if I write the gamma K, gamma L on this side. So think of this Ji, Jk, L as being an n squared by n squared matrix. The row is indexed by I and J, and the column is indexed by K and L. Think of this expectation value, gamma I, gamma J, it's just a list of numbers for each choice of I and J, as being a vector in n squared dimensional vector, where indexed by this I and J. I think of this KL as also being a vector. So this is a vector matrix vector product. And we know that this is bounded by the operator norm of this matrix, Ji, Jk, L, regarded as a matrix, like this J regarded as a matrix, not regarded as some tensor. And times then the L2 norm of this vector Jij and the L2, expectation gamma I, gamma J, and the L2 norm of this expectation gamma K, gamma L. These expectations, these L2 norms. Now we have some bounds. We have a bound. This Ji, Jk, L it's a random matrix. It's a random matrix of size n squared by n squared, whose entries are chosen from a particular distribution. And it turns out then that its operator norm, standard random matrix theory, is of order 1 over n. It's of order 1 over n. This gamma ij, its L2 norm, you can just work it out for what it's for a Gaussian state. It's always at most square root n. This one's always at most square root n. So the result is at most 1. So when you put in these states, that's the best you can do. You only get an energy of order 1, and it's with high probability. But the with high probability is just because the random. This is actually a thing you can verify quickly, because it's just, oh yeah, we know that with high probability the largest eigenvalue of this matrix is at most 1 over n, and it's a polynomial size matrix, so you could go compute it. So you can actually quickly check for a specific instance. Oh, there's no good Gaussian state that does better. What I just put out recently is kind of an extension of this to higher orders. What you can do is you can show that starting from a Gaussian state, not only does it have a small expectation value of energy, but if you look at expectation values of powers of the Hamiltonian, just like I looked at expectation values of powers of the Hamiltonian here, if you look at expectation values of powers of the Hamiltonian in a Gaussian state, you can do a similar way of thinking of them as products of matrix vector products. And again, bound it and show that it's not too big, and show that, yeah, actually, not only the Gaussian states don't have good energy, but they don't even have any good projection onto the higher energy states. So that's really a limitation of Gaussian states for these models. Then, okay, so so the Gaussian states are not good variational states. Before talking about what is a good variational state, let's turn to the sum of squares proving the bounds on the energy. And at degree 4 sum of squares, it's a degree 4 Hamiltonian. It turns out degree 4 is fooled, and degree 4 SOS sum of squares is just only proves that the Hamiltonian is at most O of n. It only proves that the norm of it is at most O of n. It doesn't get to the O of square root n. And the way you show that is actually the primal. You write down a pseudo expectation. And essentially the only pseudo expectation you can think to write down, if you didn't have any guess, is to say, the pseudo expectation value of an operator is going to be, I'll just define it to be, if the operator is most degree 4, is going to be defined to be the trace of O times 1 plus a constant times the Hamiltonian. And that's just, that's a function of the operator. And you can pick the constant such that this still gives a positive semi-definite pseudo expectation with high probability, and such that it gives you an expectation of order n. So it's like, okay, we can't do well enough. There's this pseudo expectation we get full of degree 4, but degree 6 is able to say something. It is able to determine that H is at most square root n. So it is able to provide this upper bound proof with high probability. And the way it works is kind of interesting. what you do is you say, we'll introduce some variables tau I, and tau I will be defined to be ji, jkl, gamma j, gamma k, gamma l, summed over jkl. And then h is gamma I, tau I. And then it's like the inner product of gamma with tau. And one thing sum of squares knows is Cauchy-Schwarz. When I say it knows it, I mean, it's like when you go through all the different manipulations that sum of squares can do, it's able to work out things like Cauchy-Schwarz. And so it knows that this is less than, it knows that the expectation value of h is less than the expectation value of gamma I squared times the expectation of tau I squared. The expectation value of gamma I squared, oh, sorry, square root of that, of course, square root of the expectation. The expectation of gamma I squared is just square root of n, right? Because there's n choices of gamma I. And then the expectation of tau I squared, at this point, you have to do a little algebra. Tau I is a degree 3 thing. When you take it square, it looks like degree 6. However, because of these Majorana anti-commutation relations, it winds up being only degree 4. So this is actually a degree 4 thing. And this degree 4 thing, well, you might think, uh-oh, we're like kind of back to where we started. We're like bounding the expectation value of h times square root n times the expectation value of a degree 4 thing. But this degree 4 thing has now become much, much nicer than we started with, has some particular form that a kind of straightforward bound, actually kind of similar to the one I used for the Gaussian state, based on saying something about the operator norm of H as a matrix, is able to bound this by order 1. Because it's a much simpler degree 4 thing that has a particular structure where it's able to bound it. And so the sum of squares is able to upper bound the expectation value in this way. So it really has to go to degree 6. It goes to degree 6 because it's looking at these taus, which are degree 3, and it's looking at the squares of them, which are degree 6. And that means also corresponding, there's a decomposition of H as a sum of squares of gammas and taus, which is able to prove this, this bound. I said correspondingly, there's a quantum algorithm, the quantum variation algorithm. And interestingly, the quantum variation algorithm is highly inspired by this decomposition from the sum of squares. And this is the only way I know to construct a variational state for the SYK model, which gives reasonably good energy. I know no other way to do it. And so I really, I don't know if there's anyone listening coming from the high energy community, but I'm curious if this has any application, because it's the only like simple way I know to construct a quantum state, which has that you can construct efficiently on a quantum computer that has a good expectation value for the energy. And so the thing is, these tau operators are really complicated. They're degree 3 operators. They obey some complicated commutation relations with each other. The anti-commutator of one with itself, the anti-commutator is some degree 4 operator. But suppose you like pretended for a second that the tau operators were actually obeyed the much simpler commutation relations that were the Majorana anti-commutation relations, like tau I anti-commute tau j was like delta ij times something. That something will now depend upon n in it because of how we've normalized. But imagine that they were like Majorana operators. Imagine that they were like that. Well, then this H would actually be a free fermion thing, and it would be easy to find the ground state. Well, of course, it's not. They don't obey those anti-commutation relations, and so we don't know how to find the ground state. But let's do the following thing. Let's introduce some more operators, eta I, and the eta I really are going to be just Majorana operators again. They're just another set of Majorana delta ij, like that. And let's start with the Hamiltonian H naught equals gamma I eta I. So this is a really simple Hamiltonian. It is a quadratic Hamiltonian, and we can find the ground state of this Hamiltonian. And we can efficiently prepare it. We can, like, on a quantum computer, it's been an enormous amount of work finding more and more efficient ways of simulating fermionic models. We can efficiently prepare this ground state. And now let's say someone said, okay, so I want to start with this Hamiltonian, and then I want to turn it into somehow gamma I tau I. I want to like rotate from one to the other. Well, if these tau I were also obeyed the same Majorana anti-commutation relations, rather than this much more complicated one, what you would do is you would take some Gaussian state, which is the ground state of this H naught. Maybe I shouldn't call it H naught, but I did. So you take some Gaussian state, which is the ground state of H naught, and you would apply a rotation operator. And the rotation operator would be some e to the I theta, eta I, tau I, summed over I. And it would rotate those eta variables into the tau variables. So if those taus really obeyed the Majorana anti-commutation relations, if you applied such a rotation to the ground state of this, you get the ground state of this once you took the appropriate choice of theta. And it would be like, I don't know, pi on 2 or something, except we've put these extra factors of n in our definition of what the commutation relations of the tau I should be, but there'd be some appropriate choice of theta, which would make it work out. So this is like so this would be the inspired variational state. You might be like, okay, this is the one for a particular value of theta that I'd like to pick. And this is something we can prepare again, because you can prepare this state, and this is evolution under a certain Hamiltonian, time-independent Hamiltonian, degree 4 in these, degree 3 in the gamma and degree 1 in the eta for a certain choice of theta. And the theta is not too long. So you can efficiently evolve this on a quantum computer and get some variational state. And what we were able to show is this variational state has an energy of order square root of n. And how do you show that? Well, you show it has a lot of algebra involved, but what you show is that, like, to linear order in theta, the energy gets better and gets better in exactly the way you would want. And then you bound how badly things get at the quadratic order, and that involves bounding some operator norm of, like, oh, how large a term arises at how higher order and how bad it can be. But it's interesting to me. It's like completely inspired by the sum of squares method. These tau variables are sort of like clearly important for this SYK model. I think if any people from the high energy community are listening, I think they're like what they call merons in that field. And you can now efficiently prepare this variational state, and it's a sampling task for which, there's a quantum algorithm. We don't know a classical algorithm. Like, you randomly sample something from this distribution, and then you can certify some property of it efficiently on a quantum computer. You can almost, when we proved that this gives a good variational state, we only prove it with high probability. We bound like the norm of some higher thing. The proof involves bounding the operator norm of certain things, and the bound of that holds with high probability for the SYK model. So yeah, so let me kind of summarize here. I hope I've managed to convey some of the excitement to this method. It's a completely non-perturbative method. It's been used a lot classically. There's a lot of other authors who have thought about various forms of it quantum mechanically, and you can look at some of our papers for references to then look up all that if you want to get started on that literature. And it seems to do some very interesting stuff for the SYK model. And I think some interesting open questions are, like, will it certify things at higher order of the SYK model just using the methods in our paper? That is, if you look at the SYK 6, SYK 8, I know that the worst case to the 6 you can't certify anything for, but for the particular SYK 6, it looks like our methods are able to certify non-trivial bounds, but not tight to constant factor bounds. But perhaps that's all we were able to show. Perhaps it actually does certify tight to constant factor, or perhaps an even higher order the sum of squares would certify it. Similarly, there's been some other people have done similar follow-up work, related work on sparse methods, and so whether these kinds of variational states can be useful on other Hamiltonians. Whether this can be useful for real, like, practical models, can this be a way to prepare interesting variational states for real practical models, or an important classical simulation algorithm for practical models? And does this, have any connection to these questions in quantum gravity, string theory, et cetera? I don't know. So let me just pause here and take questions. Thank you.
Thank you, Matt. So if you have a question, please unmute yourself and ask a question. Perhaps I could start. So this rotated Gaussian state seems to be working remarkably well. What happens if you take mixtures of Gaussian states? That they obviously fail to be because Gaussian in general. What happens there? Do you also get constant energy lower bound, or you get something better?
You mean, can we improve by starting with a mixture of Gaussian and then applying this? Yeah, because the other thing I was mentioning earlier was, if you just start with a mixture of Gaussians as a variational state, and then you can, on a classical computer, compute it. Let me just get to your question, but yeah, I'll just mention that was the one. If you just had a mixture of Gaussians, it seems that the energy is still at most of order 1 until you have a large number of terms in the mixture. But there's some catch in the proof that possibly if there's some bad failure of orthogonality among the mixture, so if you have some, like, mixture of Gaussians, which are almost such that they're almost parallel to each other and kind of like the norm almost cancels out, it then gets hard to prove. So there's a little bit of an open question there because that's still something you could do polynomial on a classical computer. Yeah, I don't know here. If you started with a mixture of Gaussians, whether you could potentially improve. And then now at this point, you're really wanting to ask, like, can we get arbitrarily close to the true energy? And I don't know. Yeah, we get something that's within. There's a conjecture for the exact energy. We get something that's within a constant factor of it. It's a very good question. You probably could get closer and closer. I don't know, like, whether. I don't know. I mean, I might guess that having just one or two Gaussian states probably has no improvement, simply because, like, you've only added like a constant factor of stuff and there's n degrees of freedom. But maybe taking n or n squared, some polynomial number, and applying it may lead to an improvement. Maybe also adding some higher terms in there. So I don't know. It's an interesting open question.
Any other questions?
Is there something in chat?
I don't know.
Okay, what would you recommend? Yeah, okay, no, I appreciate the question. The question, while interesting, a lot of this content was about my current ability to understand. What would you recommend for someone to look at who is pretty new to all this? Yeah, I mean, let me partly take the blame for that because I don't know if I explained it well, but I think when there's two different things I talked about. One is sum of squares, and in a sense, sum of squares, I want to say, I think the literature is way more intimidating than it actually is, because all it really comes down to is realizing that, oh, if you can somehow find a way to write the Hamiltonian as a sum of operators that are non-negative, the Hamiltonian is non-negative. Or if you write it as a scalar plus a sum of operators that are non-negative, the Hamiltonian is at least that. And there is a lot of stuff beyond that. People talk about the fooling and so on. But really, that's a lot of what it comes down to. You have to know what a semidefinite program is, and Wikipedia actually gives you a reasonable answer to what a semidefinite program is. So just look up that. And then there's I would recommend there's this. I'd have to look it up, but there's the website might be called something like sumofsquares.org, but it's like proofs and beliefs through the lens of the sum of squares algorithm. There's this absolutely amazing website that's lecture after lecture. Beautifully written down and so on, which gives all kinds of explanation of the classical version of it. But the quantum one is really not too different. So it's okay. Someone just put it in. Great, thank you.
Yeah.
Sorry, great. So that's but when it comes to applying it, the actual applications, there's a ton of math, but the actual application in quantum, most of what it relies on is fairly simple math. You have to know what a semi-definite program is in a duality, but it's. That takes a little while to learn, but otherwise, and then the SYK model, yeah, I mean, I'm just kind of I'm also partly kind of learning about the SYK model myself, and it seems to have a lot of weird properties. We have some references in our paper. I guess just the takeaway is that it's this incredibly entangled model. The energy kind of has. My key, by the way, I didn't say it, but like my mental cue for remembering how the SYK model energy works, like where the square root n comes from. So if you compute expectation h squared in the maximally mixed state, just in the maximally mixed state, you get something of order 1. So it says like, oh, the variance of h is of order 1. But actually the mental cue you should have is you should think that h actually is a lot like a Gaussian random variable itself. That is that the energy eigenvalues of h are actually Gaussian random variables. And if you pick a random eigenstate of h, its energy is going to come from a distribution that's like, let me write it down here, e to the minus e squared over some constant. So it's just coming from like a Gaussian distribution like that. That's my mental cue for like what the energy distribution is, which is kind of a remarkable property. That's like not how normal Hamiltonians go. And so then why is the energy of order square root n? Well, it's because there's 2 to the n states, And so you get exponentially many trials from this Gaussian distribution. And so when the energy is of order square root n, that's where you're exponentially unlikely to see that. That's kind of the mental cue for what the okay, it's a little more sophisticated than that, and you have like Q binomials and so on, but it's, that's like a good mental image for what's going on. There's a huge literature that I don't know about it. And I partly keep giving this talk because I keep hoping that someone in high energy is going to come to me and say, oh, I heard you're talking. Yeah, what you're writing down is dual, gravity dual to that. I'm like, okay, cool. So it's probably because I think it sounds more intimidating than it is. It's actually pretty simple. There's just because it's a little new. So. Is there a related sampling question in SYK models? So what do you mean sampling question? Like sampling from, not quite sure I understand the question here. We're talking about, mostly I was talking about sampling stuff from the SYK model and asking what its probability, what the energy is. And with high probability, the energy is a certain number. At least we prove. This is actually the funny thing is this is actually the first full proof that the energy is, there was this old proof that with high energy, the largest eigenvalue is at most something. This is actually the first full proof that with high probability, the largest eigenvalue is at least something. It comes from the existence of this quantum variational state. Although, as I say, there's a non-rigorous proof that's believed to give like the exact value. But this is like this is actually a rigorous proof that it's within this range.
When you say non-rigorous, you mean there's some, what's non-rigorous?
Oh yeah, what it is, it's some like, yeah, so it's basically cheating about an order of limits. Like you look at these moments of H, and you can kind of, that I started with, you can kind of like look at higher and higher moments and guess how they should go. Just like you can do random matrix theory in a diagrammatic way by looking at powers of H. You can do it similarly here, and you can get a guess for how it could go. The trouble is, once the power gets high enough, you start losing control because there start being too many terms in the sum. But if you kind of ignore that and reverse the order of limits from what it should be, then the order of limits being n going large and the power going large, then you get it, and it's almost certainly the exact answer. But there's some terms you don't control in the sum.
I see. Well, thanks. There's a question in the chat. Do you have any thoughts on the recent wormhole simulation in the SYK model?
Yeah. I don't. I've been following it. I don't have any thoughts on it. Let's see. Yeah, I mean, I'm sure they didn't actually create a wormhole, but I mean, like what I know is from like reading blog posts and stuff. So I'm not. I'm kind of trying to follow it, but yeah, whether there are endless variations of SYK model, and I don't know if you need to like have some particular variation of the model to see that wormhole, like, because it was like 2 different models with, I don't know. So I don't know whether these methods can start to shed light on that or not. So no comment, but it might be an interesting question. There's a lot of variations up the model.
Can I ask a question?
Yeah, sure.
Yeah.
Hello, thank you for the talk. Just a simple-minded question. Apart from the relation to wormhole, is there any reason, because in various points you mentioned gravity, is there any reason that you think that this method would be useful for quantum gravity or something like that?
Yeah, I don't know. I mean, I know this SYK is supposed to have a dual, right? And I know that dual is supposed to be related to it, but I don't know if this method itself can be useful for it. I mean, this method is kind of very tied to the Hamiltonian formulation, and maybe that's the weakness. I've been thinking a little bit about whether there's ways of going beyond the Hamiltonian formulation. I mean, as here, we're really talking about like, here's a Hamiltonian, and then often that Hamiltonian is supposed to be dual to some like gravity theory in a bulk or something like that. But I don't know if there's a way of like taking the sum of squares and going beyond Hamiltonian directly. I just, I guess just, I mean, maybe I'm being guilty of the thing. like there's that like saying like, oh, quantum mechanics must have something to do with consciousness because we don't understand quantum mechanics, we don't understand consciousness. So, maybe I'm being guilty of the same kind of thing. I'm like, oh, the SYK model is highly entangled and non-perturbative, has something to do with gravity, and this method has something to do with non-perturbative solutions, so they must have something to do with each other. I might be like guilty of that, but I don't know. Yeah, I don't have any. I feel there's something there, but I don't have a strong answer. And I feel one thing might be to like think about non-Hamiltonian versions of the method, but I don't know.
Thank you.
I mean, it's a great question. It's just I don't know. I don't have a good answer to it, but I'm thinking about it.
So I guess perhaps last question. So what about Hamiltonians beyond SYK? What do you reckon would be other interesting Hamiltonians that would benefit from this SOS treatment?
Yeah, well, I mean, one thing I've been thinking a lot about is models in quantum chemistry, and it's been applied. It's been applied. There's a few people that have been working really hard to apply it for models in quantum chemistry as a classical simulation algorithm. I think it's kind of an interesting target because when you look at a lot of the models we consider in physics, like the Hubbard model, they have this extra locality. And there are versions of the sum of squares that take into account locality. You might decide, oh, in the pseudo expectation value, I'm going to keep track of all degree 2 things, all degree 4 things. The higher degree, the more effort it is to keep track of, but then the more powerful. But you might then say, well, I'm also going to keep track of degree 6, but only degree 6 within a little local patch. And so it won't be too much harder. And since the model is local, that's the most important ones to keep track of. So that's one way to go. And people have thought about things like that, keeping track of like pseudo expectations that are higher degree locally to take into account locality. But if you talk about the sort of completely non-local version, then it doesn't seem as adapted to the Hubbard model or some other local model in condensed matter physics. But there are these models like the models in quantum chemistry, which are very non-local. They're like all interacting with all. So I kind of feel they're a very natural target. And people have applied this method to it. You'd have to read the papers. I don't want to comment on, some things seem promising and some things seem less promising. And it's partly because, it's a powerful method, more powerful as the order goes up. But unfortunately, on present day classical computers, doing degree 4 already gets kind of time consuming, although possible. And degree 6 in full generality is going to be extremely difficult, except on small molecules. So you start thinking like, can you do fragments of degree 6 and not all of it? So I've been looking at things like, oh, can I do a fragment of degree 6 that involves inspired by these tau variables? And I think it's an interesting question. I don't yet have the results I'm happy with, but I think like for a practical target, I think like that's a very natural practical target.
I guess for fragments, you want to identify those terms that are somehow contributing more than others.
Yeah. So that you, rather than solving like the full degree 6 sum of squares thing, which would be a rather big semi-definite program because it would be a matrix of size n cubed by n cubed, you might want to solve just part of the semi-definite program. Just remember certain things being positive and certain linearity constraints. And so, for example, in this case, these tau variables, yeah, the full degree 6 sum shows it, but there's a much smaller semi-definite program that can show it. There may be smaller versions of this sum of squares, smaller semi-definite programs that can be solved quickly, practically, that still carry a lot of useful information. So I feel like quantum chemistry is a natural target.
Okay. Thanks, Matt. So there are no further questions, and thank you, Matthew, for giving us this wonderful talk. It was great, fun to hear about it, your results. And well, stay tuned for other announcements for our seminars that will carry on. So that would conclude our colloquium. Thank you, everyone, for joining. Thank you, Matt, again.
Thank you.
Thank you.
Thank you. Bye.
Bye.